A neutron star is an incredibly dense and compact object that forms after the core collapse of a massive star during a supernova explosion. It is composed almost entirely of neutrons, which are subatomic particles found in the nuclei of atoms and are themselves composed of quarks held together by the strong nuclear force. Composition. Neutron stars are so dense that their matter is packed incredibly tightly. The gravitational collapse is so intense that electrons and protons in the core of the collapsing star are forced to combine to form neutrons and neutrinos. This process is known as neutronization or neutron capture. The outermost layer of a neutron star is composed of a thin atmosphere made up of electrons, protons, and a small number of heavier ions. However, beneath this atmosphere, the neutron star is primarily composed of a superfluid neutron fluid, which is a dense collection of neutrons that behave as a quantum mechanical fluid with almost no viscosity. This neutron fluid is surrounded by a solid crust made up of atomic nuclei, iron and heavier elements, embedded in a sea of electrons. The interior of a neutron star is even more exotic. As you move deeper into the star, the pressure and density increase significantly. The inner core of a neutron star is believed to be composed of a state of matter called neutron degenerate matter. In this state, neutrons are packed so densely that they begin to exhibit quantum mechanical effects on a macroscopic scale, and the distinction between individual neutrons becomes blurred. Gravity. Neutron stars have an incredibly strong gravitational pull due to their mass and compact size. The escape velocity from their surface is a significant fraction of the speed of light, making them highly dense and massive objects. Extreme density. The density inside a neutron star is astonishingly high, on the order of several times that of atomic nuclei. This density is what allows neutron stars to have such strong gravitational fields. Pressure and equations of state. The pressure in the core of a neutron star is sustained by the neutron degenerate matter and the repulsive strong nuclear force between neutrons. The equation of state that describes the relationship between pressure, density, and composition under such extreme conditions is a subject of intense research and theoretical modeling. Neutrino emission. Neutron stars are extremely hot when they form, but they cool down over time through various processes, one of which is the emission of neutrinos. Neutrinos are nearly massless particles that interact very weakly with matter, allowing them to escape from the interior of the star and carry away energy. Magnetic fields. Neutron stars often possess incredibly strong magnetic fields, billions of times more potent than those on Earth. These magnetic fields can give rise to intense radiation emissions, such as X-rays and gamma rays, as charged particles are accelerated and emit radiation in the presence of the magnetic field. Quark matter hypothesis. In the most extreme conditions at the center of a neutron star, it's theoretically possible that quarks, the building blocks of protons and neutrons, may merge and form a state of matter known as quark matter or quark-gluon plasma. This is still a topic of active research and speculation. It's important to note that our understanding of neutron stars is based on theoretical models and observations of their behavior and emissions. The extreme conditions inside neutron stars make them challenging to study directly, but advance in astronomy and theoretical physics continue to deepen our understanding of these enigmatic objects.